In this sixth module, we are discussing weak interactions. In this sixth video, we will talk about the properties of the Z boson, which transmits the neutral weak force and can be considered as the heavy brother of the photon. After following this video, you will know its properties, its mass and the way to measure it, and its couplings to matter. In video 4.5, we have already discussed the prototype process E plus E minus goes to mu plus mu minus for the production of fermion pairs by electron-positron annihilation. In addition to electromagnetic interactions, as shown in the left graph, this process can be mediated by neutral weak interactions, as shown in the right graph. Since initial and final states are the same, one must add the amplitudes. In the cross-section, we thus find three terms to lowest order. The first term, sigma gamma, contains the square of the photon exchange amplitude, the second one, sigma z, that of the z exchange, and the third one, sigma int, the interference between the two. For the photon alone, we already quoted the cross-section in video 4.5. The total differential cross-section, which also takes into account the other two contributions, contains a term symmetric in the scattering angle theta, like the one we had found for the photon. The scattering angle, I remind you, is the angle between the incoming E minus and the outgoing mu minus. The coefficient A0 of this term now contains a new contribution due to weak interactions. There is also an additional asymmetric term proportional to the coefficient A1. The coefficients contain the real part and the square of a resonance term R, which comes from the resonant production of Z bosons when the total E plus E minus energy approaches the Z mass. It contains the Breit-Wigner function characteristic for the propagator of massive virtual bosons. The coupling constants GV and GA depend on the electric charge and the weak isospin of the matter particles involved in each vertex. Due to the value of the weak mixing angle, sin squared theta roughly equal to 1/4, GV has a small value for charged leptons, GA is simply -1/2. At low energies, square root of S much less than mz, where R is roughly equal to 0, the influence of weak interactions is negligible. We fall back onto the result found by electromagnetism, that is to say A0 equal to 1 and A1 equal to 0. The terms proportional to the real part of R are due to electroweak interference and are important in the intermediate region where neither the photon nor the Z exchange are dominant. And finally, close to the Z mass, where the terms proportional to R squared dominate, we find that the weak interactions is 2 orders of magnitude stronger than the electromagnetic one due to the amplification by the resonance. The Z resonance manifests itself by an enormous peak in the total cross-section. Electroweak interference causes a large angular asymmetry on the flanks of the resonance. At low energies, the cross-section depends on the electromagnetic coupling alpha and the square of the center of mass energy S, like sigma equal to 4 pi alpha squared divided by 3s, the characteristic size and shape of purely electromagnetic interactions. As the energy approaches the Z peak, we see an enormous increase and weak interactions dominates the process, thanks to the resonant exchange of Z bosons that we now may call almost real instead of virtual. Far above the resonance, the two processes add up and are of comparable size. The interference term introduces an asymmetry into the angular distribution, which we had already noted in video 4.5. To quantify it, one defines a forward-backward asymmetry AFB, comparing the rate of forward, theta less than 90 degrees, and backward, theta bigger than 90 degrees scattering. This asymmetry is large and negative below the resonance, goes to 0 at S roughly equal to mz squared, and becomes large and positive above the resonance. In the immediate vicinity of the Z resonance, that is to say a few Z widths away from the Z mass, we can neglect both electromagnetic interactions and electroweak interference. For all E plus E minus interactions into a pair of point-like fermions, we then obtain a cross-section with a peak given by r squared. In this region, the Z boson is quasi-real. The maximum of the cross-section can be expressed in terms of the decay width gamma z of the real Z boson. The partial width of the Z decay into electrons and other fermions depend on their weak and electromagnetic charges T3 and Q, as shown on the left. In addition, the number of colors Nc comes in for quark final states. The partial and total width can be derived from the shape and height of the measured cross-section for all fermion species with a mass smaller than half the Z boson mass. This even includes neutrinos, which are not seen in the measured final state as any other invisible particle. In this way, experiments have fixed the number of neutrino species with mass of the neutrino less than mass of the Z divided by 2 to exactly 3 with very high precision, as you can see in the graph on the right. There are thus only 3 generations of light matter. The position of the peak determines the mass of the Z boson with high precision. Here we show the results of the 4 experiments at the CERN Large Electron-Positron Collider, LEP, the predecessor of the LHC. The mass determination by the resonance method is precise to 2 parts in 10 to the 5. This accuracy would correspond to a measurement of my own weight to about 2 grams. This may not sound very impressive, but my lifetime is hopefully of the order of 2 billion seconds, and I weigh about 10 to the 5 gram. The Z boson lifetime is 3 times 10 to the minus 25 seconds, and it weighs 1.6251 times 10 to the minus 22 grams. At such a level of precision, unexpected effects influence the measurement. As incredible as it may seem, the phase of the moon influences this measurement. Just like seawater, the Earth's crust goes through high and low tides with a height difference of about 20 centimeters. The tidal waves deform the LEP storage ring by some millimeters compared to its total length of 27 kilometers. At constant frequency, this changes the beam momentum, and focalization amplifies this effect. Consequently, the beam energy depends on the moon phase at the level of 100 ppm parts per million. This effect has been measured using resonant depolarization, a method to determine the energy of the circulating beam with an impressive precision. You see the result in this graph, which shows the beam energy over large portions of the passage of a tidal wave. And even the passage of the high-speed TGV train in nearby France influences the measurement. Since the TGV is powered by a single-phase DC current, its passage induces parasitic currents into the storage ring. Because of their hysteresis, the magnets remember the train schedule, as you can see on the right. This again leads to a slight variation of the collider energy. All of these incredible effects had to be taken into account to arrive at the final result for the Z boson mass. This should allow you to appreciate the impressive precision with which the mass can be measured by resonant production of a particle. The method remains a specialty of electron-positron colliders, since the point-like initial state allows an excellent definition of the kinematics. The coupling of the Z boson to leptons, GV and GA, are measured using the total and differential cross-sections, as well as the polarization dependence of the E plus E minus annihilation into leptons. One finds confirmation of our choice of weak isospin as up and down members of a doublet. One also finds that all generations have the same couplings to an accuracy of a few times 10 to the minus 3. For charged leptons, the measured values of GV are close to 0 and GA close to minus 1/2, as we expected. For neutrinos, one finds GV equal to GA equal to 1/2, as one would expect for fermions with weak isospin up and electric charge 0. In the next video, we will talk about purely weak interactions, that is to say, weak decays of quarks.